Hello friends, welcome to the next session. Now we are going to complete the last problem of type 2 of finite state machine. Let's get started. So the question which is given to us is, design a finite state machine in which the input is valid if it contains at least 3 A's. Now this problem will be further splitted into two more type of problems. As of now, let's focus on what is given. The question says that the input will be accepted if it contains at least 3 A's. Meaningly, if I have number of A's as 3 or more than 3, the finite state machine should accept this particular input. So let's start. So moving to the solution, I have to prepare my state function, which I write as given a state and an input symbol, what is the next state. Similarly, we will be incorporating the machine function also inside this. So I say over here, the machine function will be given a state and an input, what is the output. Let's get started with state function by creating our S cross I table. So I have certain states S, I have some input I. Now the input is over the alphabet A and B, so I'll be writing over here A and B respectively, and there is going to be a start state QS as usual by default. Now after the start state QS, it is very important for us to understand what are the furthermore states required. Now if we introspect the problem closely, it says that we have to design in which the number of A's has to be at least 3. So can I say over here we are keeping a track of, or we are counting the number of A's? Yes. And the input will be accepted if number of A's is 3 or greater than 3. So can I say for keeping a track, I'll be keeping a track of the states, number of A's as 0, number of A's 1, number of A's encountered 2, number of A's encountered 3, and number of A's encountered more than 3. Okay, so overall I'll be having these many states, 0, 1, 2, 3 and more than 3 as the states. So let's get started. So I have my number of A's. So number of A's can be 0. Going ahead, number of A's can be 1. Number of A's can be 2. Number of A's can be 3. Or number of A's can be more than 3. Fine. So let us give the state names now. After QS, I have Q0, Q1, Q2, Q3, and finally my Q4. Now, if I observe QS, if I say the machine is in the start state, how many number of A's will it have? Of course, the input is going to be empty, meaningly the number of A's are going to be 0. Okay, so in the start state, when the number of A's are 0 and the machine encounters a single A, the number of A's become 1. And which is the state keeping a track of one number of A's? It is Q1. Therefore, the QS on receiving input symbol A goes to Q1. Similarly, when I come back to my start state QS on receiving an input symbol B, so QS is a start state having nothing on the input and a B comes across. So number of A's were 0 and they will remain 0. What is going to increment is the number of B's, which we are really not interested in keeping a track on. Therefore, the number of A's will still be 0 and therefore QS on receiving B will be going to a state where the number of A's are 0. So QS on receiving input symbol B will go to Q0. Coming on to Q0. By now we know whatever is there in QS always gets repeated in Q0. Therefore let's write it without giving a single thought about it. So I have Q0 on A goes to Q1 and Q0 on B remains in Q0. Coming to the next state, Q1. In Q1, I am having the number of A's as 1 and one A when encountered with another A for state Q1 gives me number of A's as 2. and number of A's as 2 is kept track by the state Q2. Therefore, Q1 on A goes to Q2. Similarly, Q1 on receiving a B, Q1 when receives the input symbol B, initially it had a single A, and coming across a B is not going to make any difference. Therefore, it will remain in state Q1 itself. Similarly, Q2 on receiving A, Q2 already has two number of A's and one more A comes across. So number of A's become 3. Number of A's 3, that means I have to go to the state Q3. Similarly, Q2 on receiving B, Q2 has two number of A's, it comes across B, therefore number of A's remain the same. So they were previously 2 and now also they will remain as 2. Therefore, it goes to the state Q2. In Q3 state, the number of the A's were 3 and one more A comes across. So the number of A's now become 4. So 4 is indirectly anything which is greater than 3, and for that we are keeping a track of this 4 using this next state which is Q4. Therefore, Q3 on A will go to the state Q4, and Q3 having 3 A's when receives a B will remain in state Q3. Now, if you observe the transition table carefully, we will see over here that only my A column is having the states change, whereas B column is not having the state change. The reason being obvious that the impact of B on the input is nothing. Therefore, every state when receives the B symbol will remain in that state. Let's go ahead and fill the last cell. We have Q4. In Q4, the state is keeping a track if the number of A's are more than 3. By more than 3, I mean the number of A's can be 4, 5, 6, 7 or up to infinite. So, if I say the number of A's in Q4 are more than 3, assuming let's say the number of A's are 5 and I come across one more A. So, number of A's which I have right now becomes 6. Is 6 more than 3? Yes. Therefore, Q4 on receiving A will remain in state Q4 only because the number of A's are still more than 3. Similarly, Q4 on receiving B, number of A's were initially more than 3 and one B came across, doesn't make any difference and it will still remain in the state Q4. Therefore, Q4 on B again remains in state Q4. Now, coming on to what to mark as the final state. Now, if we observe the question carefully, the question says, design a FSM in which the input is valid if it contains at least 3 A's. So can I say all the states in which the number of A's are 3 or greater than 3 can be considered as the final states? Exactly. So therefore we say over here, since number of A's has to be at least 3, so Q3 is that state and Q4 is that state which can be marked as the final state. Now let's see what machine function is going to do over here. After marking this state, everywhere we have Q3 and Q4, we are going to say that the input is valid. So everywhere we have Q3 and Q4, we'll be writing the output as yes. So yes, yes, and here also yes. Q1 no, Q0 no, Q0 no, Q1 no, Q2 no, Q2 no, and Q1 also no. Fine. So my state function and machine function is implemented. Now let's do the last step of looking at the examples, considering a positive case as well as a negative case. Let's get started. So the first example which I consider is QS on receiving AAB, AAB. So if I count the number of A's over here, they are 4. So ideally it should be accepted. Let's see whether the FSM is capable of doing the same thing. QS on receiving input symbol A is going to Q1, A, B, A, A, B. Q1 on receiving input symbol A is going to Q2. What I have is B, A, B. Q2 on receiving input symbol B is going to Q2 again. So I have Q2, A, B. Q2 on receiving input symbol A will go to state Q3. So I have Q3 and left is AB. Going ahead, I rewrite over here Q3 on receiving input symbol A will go to Q4. Therefore, we write Q4 over here and I have a B left on the tape. Finally, Q4 on B, we all know B does not have any impact. Therefore, Q4 on B, looking at the table, we see that it is in Q4 and Q4 is my final state. Since it is my final state, the output of this machine is going to be yes, signifying that the input will be accepted. Let's go ahead with second example. So, example for the reject case, I have QS BA signifying the number of A's over here are 2, so it should be ideally rejected. So QS on receiving input symbol B goes to Q0. I have ABA with me. Q0 on receiving input symbol A goes to Q1. I have BA left with me. Q1 on receiving input symbol B remains in Q1. So I have Q1 with A with me, and lastly Q1 on A is going to throw the output. So Q1 on A over here is going to go to Q2, and my Q2 state is giving the output as no. That is, the number will be rejected since the number of A's are lesser than 3. That completes the problem. See you in the next problem. Thank you.